Okay, this is Maple, and we are doing derivatives and higher derivatives. So let's start with defining a function. If you want to define a function f, colon equals x goes to, that's a minus sign with an arrow, with an upper, with a greater than sign. Say x cubed times the sine of x over, I don't know, log of x. That's a nice function. What does it look like? Of course, the log's only defined for x positive, so let's plot f of x, the x going from 0 to 10. So of course, actually, maybe I should have started from 1. Of course, log of 1 is 0, so there's some strange behavior there. Maybe I'll make it log of 1.1. Okay. So here we have this interesting function. And what is the command to differentiate a function? It is d of f. So d of f is this somewhat complicated function. Suppose we want to compute the tangent line at the point I don't know, 6, comma f of 6. So let me just call this TL for tangent line, colon equals. So you always remember the formula for the tangent line to a curve at a point. It's the derivative of the function f evaluated at x equals 6 times x minus 6 plus the value of the function at 6. That, complicated as it may look, is the tangent line. So let's say we want to go back and now plot the tangent line and the curve together. So if I'm plotting two functions together, I put the two functions inside curly brackets. So one is the original function, the other is the tangent line. And here's this beautiful picture of the red is the curve, and at this point x equals 6, there is the tangent line. Let's see, if I want to sort of blow this up a little bit, let me just maybe graph this from, I can also put limits on y. Maybe y goes from minus 100 to 300. Oops, we got the y. There we are. So here is this interesting curve. There is the tangent line. Now, what about computing the second, third, and in general, higher derivatives? So, oops, this is a sharp sign, means it's just a note. So the derivative of f is the derivative of f. That's the first derivative. The second derivative you get by differentiating the first derivative. So let me just say, the first derivative is this. The second derivative, which means differentiate the derivative, is that. The third derivative, well, you could write it as the derivative of the derivative of the derivative of f. And it's getting more and more complicated. Now, and you can keep iterating this procedure to get as many derivatives as you need. But if for some reason you wanted the 20th derivative, that's a little bit complicated to write out and it's not necessary. So syntax to compute the nth derivative of a function it is in parentheses d, above the 2, shift 2, there's this at sign, at n of f. That's the nth derivative. That's the command to get the nth derivative. So for example, if we wanted the second derivative of f, so maybe it's right over here. This is the syntax d at n of f, and evaluated at x, it's that. Exactly this. Let me evaluate this at x so you can really compare them. This is the first, here's the second derivative. It's exactly this. How will we get the third derivative? This is what we want to compare it to. This and this, lines 6 and 8. They're the same. Suppose for some reason you wanted the 10th derivative. Well, it's kind of messy, but that's what it is. Let's define a new function. Let's say maybe f is going to be, I'll call it g. G will be the function x goes to x times e to the x. The way you write the exponential function is exp of x. Do not write e to the x. That's wrong. So this is my function. The first derivative evaluated at x is that. The second derivative of g evaluated at x is that. The third derivative is that. Oh, you see kind of a pattern. It's like x e to the x, 1 times e to the x plus x e to the x, 2 times e to the x plus x e to the x, 3 times e to the x plus x e to the x. Let's see if there's a pattern. We can make a loop that will just calculate a lot of derivatives of f. By the way, what happens if I put a 0 here? I just get back the original function. So the convention is the 0th derivative of a function is just the function. Let's make a loop. For n from 0 to 12, do, I always like to put my n do in. And what I want to do is compute the nth derivative of the function g evaluated at x. And here we have it. You see, every term involves x e to the x preceded by 0 e to the x, 1 e to the x, 2 e to the x, and so forth. So you really see the pattern very nicely when you use a loop to iterate this derivative. Now, the command D is used to differentiate a function, say d of f. How do we differentiate an expression? So the difference is that, for example, this is the function h of x equals x cubed. Right? X cubed by itself is an expression, not a function. H of x is a function. D of h, evaluated at x, is 3x squared. If I write d of x cubed, I get something. It's not clear what it means, but it's not 3x squared. It has some other junk in there. In any case, it's not a function. So that's not good. The command to differentiate an expression with respect to the variable, whatever the variable is, x, is the following. You write diff, whatever is the expression, for example, x cubed, comma x, the variable you're differentiating with respect to. And now you do get 3x squared. Okay? So a function is kind of a machine. You put in a number and a number comes out. H is the function. You put in x and out comes x cubed. The expression x cubed is not a function. It's just polynomial. But it can be differentiated, and this is the command to differentiate it. Now there's also a command to differentiate, to find a higher power, a higher derivative, though somewhat awkward, and I don't recommend it. So the command to compute the nth derivative of an expression is the following. So you write diff, the expression, let's say x cubed, and then you do this sort of backwards apostrophe, the $sign backwards apostrophe, and in parentheses, the variable x and how many derivatives you want to take. So this is going to give us the second derivative. So if this works, second derivative of x cubed is 6x. It does work. But this is a kind of awkward notation. The notation we have here for the nth derivative is much more elegant. But it's important to know first that you can differentiate an expression, and you can even find higher derivatives. But in many cases, it's easier to work with a function than it is to work with an expression. An interesting problem is you like to know, for example, let's go back to the function we started with. Here it is. This is my function f, which looks like this. And if you look at this function here, it's decreasing a little bit, goes up a tiny bit, comes down, goes up, comes down. Let me go a little further out, see what happens. Oh, comes back up again. Yeah. What does the derivative look like? Let me just repeat this down here. There's my function f. D of f of x, the derivative is that. Suppose I plot the function f of x. That's what it looks like. Suppose I plot the function d of f of x. It's kind of weird. Let me plot the two of them together. So again, when I'm plotting several functions, I put them in curly brackets separated by commas. So one function is f of x, the other is the derivative. That's what it looks like. The red is my function f. The blue is the derivative. Suppose I want to know where these functions cross the x-axis. So if I want to solve the equation f of x equals 0 for x, probably not going to be too successful because it's a very complicated function. But if I want to solve it numerically, I use fsolve. And it gives me one value, but I like to find positive values. So suppose I want to solve it for x going from 1.1 to 10. What is that number, by the way? So the area of a circle of radius 1 is pi, spelled with a capital P, pi. And if I want to evaluate pi as a decimal, that's the command. That's what it is. So this function f of x is 0 at pi. Of course, if you look at the function for a moment, here's the function. Log x is positive for x bigger than 1. X cubed is positive, but sine of x, that's 0 at pi. So this first 0, the function's at pi. This will be 2 pi, this will be 3 pi, this will be 4 pi, and so on. What about for the second derivative? I'm curious where the second derivative is 0. So there we want to solve the derivative of f at x is 0. And that's 0 at 1.34. I guess that's the point around there. It's also 0, sorry, yeah, it's the blue curve, somewhere between 5 and 6. Let me look for that 0. Yeah. 5.1. And here, there are lots of zeros. And in calculus, you know, or you'll learn, or you'll remember, to understand the graph of a function, it's important to know the critical points where the derivative is 0 and the inflection points where the second derivative is 0. So we'll have more with that shortly. Okay. Anyway, so what we've done so far is discuss higher derivatives of a function. I also want to explain how to construct a composite function in Maple. So for example, suppose f is the function x cubed. And suppose g is the function sine of x. So the composition function, let's say f composed with g, is f of g of x. So you put sine x in here, you get sine x cubed. If you compose functions in the other way, g of f of x, sorry, is the sine of x cubed. The notation in Maple for constructing a composite function is f at g. So you put that in parentheses and calculate that at x, and it's sine x cubed. Similarly, if I want g composed with f, g at f of x is the sine of x cubed. So f at g mean this is the composite function. So f at g of x is equal to f of g of x. And in the homework, in homework 5, there's some exercises to compute some things using composite functions. What is the derivative of f composed with g of x? So when you learn the chain rule, when you use the chain rule, f composed with g is the sine of x cubed, and the derivative is 3 sine of x squared cosine x. So this is the chain rule. Okay, that I believe is everything I wanted to put into this lesson. So we are done.